Okay, so this is basically tutorial 1 of the tutorial 1 of measure and integration. Measure and integration. This is course MA68. I think I'm not able to know the exact name, but okay. So I'll start with one problem. Today I am not able to get the problem in. I have to write the problem, and from the next class I'll try to take picture of those problems and try to paste here. Okay, so first question is that let x be an uncountable set. Uncountable set. Let R be the collection of all at most countable subsets of X, including the empty set, including empty set, so that R is a ring. Uh, Question is second is that is it sigma ring? First question. Another one is that is it a sigma algebra? So first we will see what is a ring and definition. I will recall definitions of what is ring and um, what is ring and what is the sigma algebra and what is sigma ring. Okay, so definition is clear. Okay, so definition says that if I take a collection of subsets, it will be ring if it is closed under union and it is closed under. So let me write once then, just two for the union and difference. That's true. Yeah, if it is closed under union and it is closed under difference, uh, then it is called a ring, and it is called sigma ring if it is closed under countable union, and it is called sigma algebra if it is closed under um, if there is X, the full set, the full set is there, full set is there. So let me write on that. So a subset. So let's recall the definition of ring. What it says, a subset, a set of collection of subsets of X, a set. I think usually it is using the symbol R, a set R, a collection R of subsets of R, a collection R, of subsets of X is said to be ring, is said to be ring if it is closed under, union and differences. So that means if we have two elements E and F in that collection R, so then this should imply that E union F and E set difference F should belongs to R. This is the two condition required. So here it is said that the collection here it is taken. R is the collection of all collection of all utmost countable subsets. So R is the basically R is the X subset of. So let's take E is the subset of X such that E is at most countable. subset of X. So therefore, if we take two set E1 and E2 in between R, so therefore it is clear that E1 union UT that is again countable because E1 and E2 both are countable because they are the elements of the set R. So therefore they have to be the countable because by the definition of the elements, then you need to be again countable, and that implies that E1, E2 be an element in R. First and second is that similarly E1 minus E2 that will be again countable because E1 is countable because this is subset of E1. That implies that as E1 is countable, E1 is at most countable or countable. E1 is at most countable. That implies that then E2 then E1 minus E2 that will be in X. So that implies that R is a ring. First condition closed. Second is that whether it is sigma ring or not. So sigma ring definition, sigma ring, a ring is said to be sigma ring if it is closed under countable union. A ring is said to be sigma ring if it is closed under countable union. Closed under countable union. Okay. Now if I take a set countable set I equals to 1 to infinity, be a collection of elements in be a countable collection of elements, countable collection of elements from collection from the set R, then their union, then their union EI, because we know that countable union of countable set is again countable, so therefore that is again countable, is again countable or at most countable. You can write again at most countable, at most countable. That implies union of EI I equals to 1 to infinity is belongs to R. Uh, so okay, so it belongs to R. This implies that R is a sigma algebra, sigma ring. A sigma ring is called sigma algebra. A sigma ring is called sigma algebra if the full set is in there. Okay, but that can't happen because that can't happen. But this is not the case in our situation. But this is not the case in yes, that's true. It is uncountable, so that's why this is not there because R is the countable collection. Okay, so that's R is the collection of all those sets for whose elements are at most countable. So that's why X is not here. But this is not the case in our case. In our example, in our collection, as X is uncountable. X is uncountable. That implies R is not an algebra. R is not an sigma algebra. Okay, so I must say that this is the beginning. This is the beginning of the course. So when you will go ahead after 1 week or 2 weeks, then they will see that actually everything whatever you are doing that will be in the sigma algebra. So in that case, in sigma algebra, the full set will always be there, and as well as the empty set will also be there. So these are the just beginning things. So here sigma ring and sigma, just ring and sigma ring, those things are there. But ultimately you will be only dealing with sigma algebra. Okay, so this is the first question. So now I'll discuss the second question. Second question, how do you say that? Second question say that let um, question what it says. Um, let let x be a non-empty set and let E subset of X, let epsilon is actually collection of just only collection E, compute RE. What is RE? RE is the RE basically it's the smallest. I think it is the signal. It is the ring generated by. I think symbol RE is used as the ring generated by sigma ring generated by. So what is this RE? The sigma ring generated by E. I think. Okay. Sigma ring or ring. Let me check once. Are in general denotes RE denotes just a minute. What usually are of a set usually denotes the smallest ring containing whenever is R is that is the smallest ring containing E and SE that is the smallest sigma ring containing E and whenever HE that is the smallest hereditary ring containing E. So here it is the smallest ring containing E. This is what it is asked. Okay. So smallest ring containing E. Okay. So, but as we know that if a set is ring, so then empty set will always be there. Whatever the situation it is, empty set will always be there. Why the empty set will be there? Because it is closed under differences. So therefore, E minus if a set is there, so there that say that minus that set will be there. That's the reason. So that's why it will be there. So so here uh, so empty set will always be there in that way. In that empty set will always be there and E will always be there because that is the containing set. So that implies that empty set and E, this is there subset of the ring generated by E. So whether does there exist any other possibility needed to be to satisfy the conditions? Because this is a whether this is let's check this is a ring. Why this is a ring? This is a ring because this is closed under differences because this is closed under differences and union closed under differences and closed under union, but this is the smallest one, so therefore the smallest ring containing E is empty set and E. Okay, so this is all. The next question, so this is the all answer, complete answer. The next question, okay, so okay, so next question says that let R be a ring of subsets of non-empty set X. Let R be a ring of subsets of a non-empty set X. Let mu be a non-negative finite and additive set functions on R if mu is continuous from above for E equals to empty set, so that mu is a measure, so that Mu is a measure on R. Measure on R. So here I will just say what is first. I will recall what is mean by continuity from above. That says let me not make any mistake. Continuity from above means that if you take continuity from above means this is the decreasing one maybe. Continuity from above means this is the continuity from above decreasing. Let so continuity from above. Continuity from above. This means that for E equals to empty set only. Okay, so that means okay that I'm saying what is E equals to empty. Let if I equals to 1 to infinity be a decreasing set, be a decreasing set. So decreasing set means E1 is actually containing E2, containing E3 that way. That is a decreasing sequence of sets in R and intersection of I equals to 1 to infinity belongs to R. Okay, if mu of En is finite for some n, I mean some n 1 to infinity in that n, then the intersection, then mu of intersection of I equals to 1 to infinity, that will be equals to limit of n times to infinity mu of En. This is means this is what it is called the continuity from above. This is what it is called continuity from above. So now the question is here the continuity from above of the set for the set E equals to intersection of I equals to 1 to infinity. So here E is equals to empty set. For that set, we need continuity from above. Okay. So so that we have the fact that this is continuous from above. So using that, we have to prove that this is a measure. Okay. So for we have to show that if um, take the question, let R be the ring of succession on a set, let me be the negative finite additive set functions on R, mu is continuous from above, so that mu is a ring. Sorry, mu is a measure on R. So mu is a measure on R man to show that mu of empty set is equals to 0 first. Second is that mu of any set that is non-negative what already given. So mu of I will change it to f greater than equals to 0 for all f belongs to the collection R, and which is already given. This fact is given because non-negative function, so that's why that is not needed. And the other is the additive, countable additive, and mu of countable subadditive, that is mu of union equals to 1 to uh, union equals to 1 to I think countable additivity actually. So if ei is the disjoint union, if I equals to 1 to infinity, the countable collection of disjoint set, countable collection of sets in R which are mutually disjoint, which are mutually disjoint, which are mutually disjoint. That means ei intersection ej is empty for all I not equals to j. Then mu of E is equals to summation of mu of I equals to 1 to infinity. So this is countable subadditivity, and this is what we have to show, and we don't need to show anything else. Okay, countable. This is called countable additivity. So So first take Fn is equals to union of I equals to 1 to n ei. I mean, let's take ei be the countable collection of sets in R which are mutually disjunct, and we have to show that uh, positive is given. Yeah, positive is given. So that's why it is not needed. Positive it is given, that's why it is not needed. And now we have to show the countable additivity only. That means mu of A equals to that one have to show. And now note that this Fn is a actually Fn is Fn is it has to be so yeah, it is given na MPI is given finite additive set. So positivity, sorry, we have to show the countable additivity, right? That is what. Okay, MP, you are asking that MP is empty zero, that how it is showing, right? Okay, are you asking about the this one, that MP is zero for MP set? Okay, so that I will do later, because if I get the countable additivity, that will maybe give. Okay, that may give actually. Okay, so let me see how countable additivity can be given. Just we have to use the what is called continuous from above, that we have to use, that we have only. Continuous from above, that case it is decreasing sequence in this. 1 minute. No. In this case, suppose P minus Fn, that is equals to union n equals to I equals to n plus 1, I equals to n plus 1 to infinity ei. Okay, and okay. As n tends to infinity, this will be giving me just 1 minute. Give me 1 minute. Count. Okay, okay, let me do it at the later. Okay, let's do the next question. I hope I need to first. I have to think. I think I have to push first prove with this one. I mean for the this one, and then I have to do something because that is needed. But I'm not able to see now. So let's do the next one. I will do the end. Obviously, there will be lots of time at the end. So um, next question. Go to the next questions, and I'll come back that one. Next question is that um, question is let x is equals to natural number n and r be the algebra of all finite subsets including empty set empty set including empty set and their completeness and their complements and their complements define for E belongs to this R. The measure mu of E is defined like this way plus infinity if E is an infinite set and zero otherwise. So what it is saying that X is the set of all natural numbers and R is taken as the collection of all finite subsets and their complements. Okay, finite subsets will be there and their complements will be there. So and for E belongs to R, the measure is defined like that so that mu is continuous from above for E equals to empty set, but that mu is not measure. So that means the counter to the above case that mu can be okay. Is it my audio is I mean I'm audible? Am I audible? Okay, okay, so okay, okay. So so here it is actually counter example to the other counter mean example in the sense that mu can be continuous from above for equals at the empty set, but need not be measure that mu need not be the measure. Okay, but it is countering to the fact that okay, so here actually I understand what I missed. I missed the additive set fact. This is what I have to use. Okay, I'll do later because I'll do later. But let's do this one, and after that I will come back to this one solution. So, so we have to show that that it is first. We have to show that. Okay, so let's complete the writing the questions. I'm not able to write the questions. So we have to show that mu is a mu. So that mu is continuous from above for E equals to empty set and but that mu is not a measure. Why this is not failing to be a measure? Because uh, it is not finite. In above case, it is written three factors there: finite and additive set. Okay, but it is not finite, so that's why. Because this one also in I think course there is an counterexample given that if the measure is not finite, in that case this countable additivity continuity from above may fail. Okay, so that is here one example you can say that but mu is not measured that I have to show. So first, let's take EI be the collection of let EI be the countable collection of elements here such that EI is converging to that means basically that means empty set is equals to intersection of EI. Okay, I equals to 1 to infinity. Okay, and EI are decreasing equals to infinity are decreasing. That is that is EI is superset of EI plus 1 for all I belongs to the natural number. Okay, So now, uh, if um, as intersection is empty set, so that means what we can say, I think here we have to use the Cantelli theorem somehow. Okay, so that means there exist EI is greater than equals to EI plus 1 if EI is infinity. Okay, so if so first claim is that there exists an I naught belongs to natural number such that E I naught is a finite set. Okay, if not, one can create. If not, one can create a sequence EI. One can create a sequence EI for which intersection of EI I equals to 1 to infinity is non-empty, because suppose EI is not finite, then one can reduce each element, one single element. If it is infinite, then one can reduce one element and get the EI plus 1. That way one can create an sequence where a common element will be there. So therefore it is say something. I don't know why everything is not. Okay, so what is the target to us? Target to us to show that mu of phi is equals to limit I tends to infinity mu of ei. Okay, this is what you have to show that mu is continuous from above. Okay, this is what I have to show. But mu of phi, according to the questions, mu of phi is 0, because if the set is empty, infinite, then it will be infinite, otherwise it is 0. So mu of phi is equals to 0. So enough to show that mu of ei is 0. So to show that mu of ei is 0, enough to show that ei are finite, or after some, after, I mean, ei is finite after some point. That is what it is means. Okay, so if ei is EI is not finite, then what is the problem? It will be, I have to show that EI is finite at some point. If it is finite at some point, as EI plus or the bigger one or the subset of that, that will be finite. That will be finite subset, and that measure will be zero. But the main point is that if EI not is finite and if it is infinite, what is the problem can occur? If EI is infinite, these are the subsets, then what problem can occur? Hmm. If EI is not finite, if it is infinite, okay, okay. I got it. I got it. I got it. So, yeah. So let me do this here from here. So, okay. So what I have to show to show that it is I have to show that this is mu is continuous from above. That means I have to show that if EI is a sequence, okay, I equals to 1 to infinity coming from R, and such that intersection of EI is phi and EI is decreasing, that this happens. So then I have to show that. Then we need to show that mu of empty set, that is equals to limit m tends to infinity mu of EI, that I have to show. As phi is empty set is equals to I equals to 1 to infinity EI, that means, and EI is superset of EI plus 1, EI plus 1. So therefore, that has to be. Then there should exist I naught belongs to natural number such that E I naught plus 1 is finite. Why that has to be? Sorry, E I naught is finite. Why that has to be? Because if for example, assume that none of them are finite. Okay, so then their intersection, as one is contained in other, so therefore their intersection will not be empty. There will be a common element always, right? Because either at least one of them has to be empty or finite in that way. Otherwise, their common element will not. I mean, there will always exist a non common element. Okay. Otherwise, because this is what happening. This is what already we have, that EI is containing EI plus one. Whatever uh, I may take, at least one place it has to be finite. Otherwise, the intersection will contain some element, because this is something you can think as a nested interval type things. If a sequence, I mean, nested intervals thing says that if we take some nested intervals, so there in that case, and their length is non-zero. So in that case, their intersection contains at least one point. Okay, and if their length goes to zero, in that case, that is contains exactly one point. But here is also the similar case. If this containment is there and all of them are empty, I mean, all of them are contains infinitely many points, then their intersection should contain at least one. So therefore, EI has to be finite. So that implies that mu of ei is equals to 0, because that is what the by definition. Okay, if e is infinite set, then it is infinite, otherwise it is 0. That implies for any mu of en, that is equals to 0 for all n greater than equals to um, for all n greater than equals to I naught, because as for all n greater than equals to I naught, en is subset of e I naught. Okay, so therefore it says that that mu of phi, that is equals to, that is in general 0, but that is exactly equals to limit n tends to infinity mu of en, because mu of an is equals to 0. I can write it here, it is as well 0, that is equals to this, because mu of p is 0 by definition. Okay, and here whatever the measure is given, whatever mu is given in that way, limit n tends to infinity mu of en, that is 0. So that's why that implies mu of phi is equals to limit n tends to infinity mu of en. Okay, so that says that mu is, so that says that it is mu is continuous from above at infinity, continuous from above at at empty set. Okay, so this is what. And the second thing is says that this is not a, but this is not a measure, so that means it is violating something. And the what is the more chance to violate this thing, because empty set is becoming 0. Okay, so and whatever the value it is getting here, it is either infinity or 0, so therefore non-negative definiteness is also here, I mean non-negativity is also here. So only possible to break the rules, that is at the countable additivity. So let's take the full set n. Okay, I think here it is set n. Okay, let's take n is there, n is r in R, because R is the algebra of all finite subsets and their complements. So as empty set is finite set, so it is there. Okay, finite set, empty set is there in R, and their complement, the complement of empty set, complement of empty, that is equals to n, that is also in the collection R. Okay, so therefore R n is there. Now just a minute. So now second thing is that I have to show now what we can write. We can write n is equals to union of n equals to 1 to infinity n. Now this set are are also in there, because they are finite set, also in our, also by definition mu of this set is equals to 0. Okay, so now, and mu of n is equals to 0, and mu of this natural number set, that is equals to infinity. But mu of n, which is equals to infinity, which is not equals to 0, and that is equals to summation of n equals to 1 to, oh, oh, extremely sorry, I'm extremely sorry. Okay, so thing is that I think from here I have muted. So here thing is that okay, from here I think muted, mm, from here. So n is the natural number, and n is the collection of natural number that is in the R, because empty set, because that is finite set, that's why this is there. And its complement, because the set R is a collection of all finite sets and their complements. So therefore as empty set is there, so its complement, which is the full natural number set n, that is also there. And now thing is that n can be written in this union of n equals to 1 to infinity n. And here this n is actually coming from the real numbers. Okay, so here sorry, not real numbers, what I'm saying, this is the relation, this is in the relation, that is the ring. So also by definition, any finite set measure this mu at the finite set is giving 0, so that's what is happening. But at the infinite set, this has to be plus infinity, that is here it is. And so but this is not equals to this mu of n. Okay, I think this is clear, right? This is very easy, there is no problem. So that's why mu is not a measure, because if it is measure, it has to be the countable subadditive. At least for disjoint collection, it has to be countable additive. But this is not the case, right? I think this is in the definition whether if mu is a measure, then this has to be the countable additive, I think. Just a minute. If mu is a countable additivity, that if EI are the disjoint subsets, then their union mu of E will has to be equals to summation of mu of EI, that is mu is not. So it is failing the countable additivity. One can write failing the countable additivity. Okay. So this is one question. So let's go to the another question. Uh, so now let S be a ring, sigma ring. The question is let S be a sigma ring. Let S be a sigma ring of subsets of a non-empty set X, and mu be a measure on S. Let EI I equals to 1 to infinity be a sequence of sets in S. Define limit n tends to infinity supremum of n tends to infinity, n tends to infinity supremum of En. This is equals to intersection n equals to 1 to infinity union of I equals to n to infinity En, and if for some n belongs to natural number, we have mu of union I equals to n to infinity ei, that is finite, then show that mu of limit supremum n tends to infinity En, that is greater than or equals to limit supremum n tends to infinity mu of En. So you can think this one because I'll take time to tell. So okay, so this is the question. So here it is said that let S be a sigma ring of subsets of non-empty set X. This sigma ring, that means countable additivity is there. Subsets of non-empty set X, and mu be a measure. It is measure, so that means it is a non-negative, and empty set it is 0, and it is countable additive for the disjoint union. And let EI be a sequence of sets in S. Define limit supremum by this way: intersection of n equals to infinity and I equals to union of I equals to n to infinity En. If for some n natural number we have that this particular measure of this particular thing is finite, so that mu of this measure of the left hand side is actually greater than equals to this I mean, mu of limit supremum is greater than equals to limit supremum of mu. This limit supremum is usual real number limit supremum. Okay, so let's think a little bit and then do it. Okay, so let's do it now. So here it is, we can consider these elements as uh, these ones we will consider as fixed thing. So let's take Fn is equals to union of I equals to n to infinity and En um, and union of Fn n equals to 1 to infinity is equals to what we call that is the limit n tends to infinity supremum of En. Okay, so now supremum of En, but we know this mu is what is that is called mu. Also given that mu of Fn, measure of Fn is finite, this implies limit n tends to infinity mu of Fn is equals to mu of limit n tends to infinity supremum of En. Basically this will be limit n tends to infinity intersects union of n equals to 1 to infinity Fn, which is equals to mu of limit n tends to infinity supremum of En. Okay, that means, but there's this Gn. Note that this Fn are actually they are decreasing. As Fn are decreasing, so limit will be infimum. Note that f of n is greater than equals to f of n plus 1. So that means mu of Fn is greater than equals to mu of Fn plus 1. That implies mu of Fn is decreasing sequence. This is positive sequence but decreasing. So that's why this limits exist. Okay. So and that implies that the limit of n tends to infinity mu of Fn that is equals to infimum of over n mu of Fn. Okay. Okay. And another way, but But note that this Fn is superset of this containing all each I for I greater than equals to this n. Okay, for any fixed n, this I greater than equals to n. That implies mu of Gn is greater than equals to mu of Ei, and for all I greater than equals to n. Okay, that is because this is subset. This is just natural. If I is subset of Fn, then it has to be this has to be old. Okay, this is very natural, and that implies mu of Fn is greater than equals to supremum of uh, mu of Fn is greater than equals to supremum of the all I greater than n and mu of ei. Okay, that implies this is not just real number, so infimum of mu of fn n, okay, over n, this is greater than equals to infimum of n supremum of I greater than n mu of ei, but this is exactly equals to limit supremum of mu of n, limit supremum of n tends to infinity mu of en. Okay, so that implies limit supremum n tends to infinity mu of en, this is less than equals to infimum over n mu of en, this is equals to this is equals to limit n tends to infinity fn that I have written, I think. Now this is equals to limit n tends to infinity mu of fn, but this is exactly equals to mu of limit n tends to infinity supremum en. This is exactly equals to limit mu of limit n tends to infinity supremum fn, and that is equals to mu of limit n tends to infinity supremum. Okay, sorry. This is an. This is en. This is en. Sorry, 1 minute. Limit n tends to infinity mu of fn is equals to limit n tends to infinity mu of fn equals to and limit supreme. This is okay. So this is means, but this is means that what I think this is what we are looking for. Yeah, this is what we are looking for. So this is done, I think. Yeah. So this is done. Mu of limit n tends to infinity supremum. Mu of limit n tends to supremum. This is greater than equals to limit. Yeah. This is done. So now we'll go back to the older one. So this problem which is just left behind. So that I will do. So let's read again the let R be the ring of subsets of a non-empty set X. Let mu be a non-negative, finite and additive set functions on R, and mu is continuous from above for E equals to empty, so that mu is a measure on R. So first I will start from here. To continuity from above means this, and I have to show that mu is continuous from above at the point at infinity. Okay, at empty set, that I have to show. But also you have to show that mu is mu of empty set is 0. So now to show that mu of empty set is 0, and if I equals to 1 to infinity be a sequence of decreasing sets. Decreasing means ei is superset of ei plus 1, and intersection of I equals to 1 to infinity, that is equals to empty, then limit n tends to infinity. I have to show that it is okay, sorry, it is given. So I have to show that mu is a measure. Okay, sorry, mu is measure. Sorry, extension. Again, I'm making same mistake. So and countable additivity. Additivity. That is, if I equals to n to infinity be a sequence of sequence of sets in R such that ei intersection ej, that is empty for all I not equals to j, then mu of union of I equals to 1 to infinity, that I have to show that summation of mu of I equals to 1 to infinity. This is what I have to show. Okay. So for this, what I'll do, let's take Fn is equals to union of I equals to 1 to n ei. Okay. And I equals to 1 to n. Then, okay, so we'll also take E is equals to union of I equals to 1 to infinity ei. So therefore, then one can easily say that this E actually Fn is converging to E. That means the full union is as n tends to infinity, limit n tends to infinity Fn, that is equals to E. Okay, that is clear because limit n tends to Fn means that limit n tends to infinity I equals to 1 to n ei, that means it is a E. Okay, this is what E. Limit n tends to infinity union of I equals to 1 to n ei, that is equals to E. Okay, this is here. So but now I will do the, I think I take the um, but okay, but if we take gn is equals to E minus fa. Okay, so then we should start from the, okay, so just to understand this one, gn equals to E minus fn, then one can say that limit n tends to infinity gn is equals to empty set. That means intersection of gn, so gn is equals to empty. Here one should note that gn is decreasing, gn greater than equals to gn plus 1, and here fn is increasing, fn is less than equals to fn plus 1. Okay, so gn is decreasing, that's why when we take the limit, that means this is intersection, this intersection is equals to empty. So but as we know that mu is continuous from above, continuous from above, that is mu of empty set is equals to limit n tends to infinity gn, mu of gn. Okay, that I can write. Okay, but mu of empty set is equals to 0. Okay, that I have not shown. Why the mu of empty set is 0? Because mu is additive, mu is additive, so therefore mu of, I can let E belongs to a set in the not take E, let's take some, here it is one set is given as X, so let's take Y belongs to R, then Y minus Y, that is empty set, that belongs to R. So now measure of this set is, just a minute, measure of this set will be 0. Measure of empty set, I need measure of empty set equals to 0, or I can write additive set. U union empty is R. Okay, that is same with you. So mu of Y in union empty is equals to mu of Y plus mu of phi. Here we have used additivity of mu. Okay, so that, but this is also same with, but this is also mu of Y. So that means that implies mu of empty set is equals to mu of Y minus mu of Y, which is equals to 0. Okay, so that's why mu of empty set is equals to 0. So but mu of Gn, so let's calculate here then again. Let's get back to there. So mu of Gn is equals to 0. Mu is additive, that is very important actually for us. So now also note that, so that means what we are getting, that limit n tends to infinity mu of Gn is equals to 0, and where Gn is equals to, where Gn is equals to E minus Fn. Okay, okay. So now also we can write E is equals to E minus Fn union Fn, that is disjoint union. So here is also disjoint union. Okay, this is disjoint union, we can write disjoint union. Okay, so one can write mu of, I mean this additivity for the disjoint union, this additivity is for the disjoint union only. Okay, so we can't use all the places. So when it is a disjoint union, then you can use the direct additivity. Okay, so this is this additivity given here, that means this is the disjoint union. When it will be the situation. Okay, so mu of E is equals to mu of E minus Fn, which is actually G, plus mu of Fn. Okay, so this is the case. And but Fn we have used there, this is additive. Okay, Fn, so and this says mu of E minus mu of Fn. Okay, okay, so okay, okay, I got it. So let me write it like this way: limit n tends to, okay, so you can write mu of Gn, that is here, and it can be written here, it is disjoint union, so summation of j equals to 1 to n mu of En. So what we get, j equals to 1 to n mu of En is equals to mu of E minus mu of Gn. Now let's take limit n tends to infinity, j equals to 1 to n mu of En is equals to mu of Ey, because this is the fixed number, so we don't need any limit here. So limit n tends to infinity mu of Gn. So now but mu of Gn is equals to 0, so therefore it will be mu of E, as limit n tends to infinity mu of Gn is equals to 0, as limit n tends to infinity mu of Gn is equals to 0. So that what we get here actually, that is equals to mu of E is equals to limit n tends to infinity, so that summation of j equals to 1 to n mu of En, which is equals to summation of mu of En, n equals to 1 to infinity. So sorry, this is Ej, this is also Ej. So this is not tough, but it is little tricky. So this is the thing. Okay, so this is the thing, this is the basically thing. So let me recall this one, what we have done here actually. So here question is that let R be the ring of subsets of non-empty set X. X is a non-empty set, and it is giving that mu be a non-negative and finite and additive set. Finite means that for any set E in element R, mu of E has to be finite, first place. Second is additive means that if we take E and F, two set in F, X and E intersection F is empty, in that case mu of E plus mu of F, this is equals to mu of A union F. This is the additivity means. And also it is giving that mu is continuous from above. Mu is continuous from above means at the point for E equals to empty. So that means if I take E equals to intersection of EI, where EI are the some decreasing sets of R. So in that case, and an intersection of EI actually the set empty set. In that case, mu of E will be equals to limit n tends to infinity. Mu of E will be equals to mu of E equals to, okay. What is mean by that? This empty set, this continuous from above means that let EI be a sequence of sets. Either intersection of EI is equals to empty. Here it is already finite is given. So then mu of empty, which is actually by definition, which is already we have proved that this is zero. Because why this is zero? Because of the additivity. As additivity, that if I take a set E, any arbitrary set E, and intersection phi as empty set, so so additivity will give here. You can look at here. So this additivity is giving me that mu of empty set is zero. So that means this gives that mu of empty is equals to limit n tends to infinity mu of E n. So this is what it is giving by the continuity from above means. Okay, so now I will use this one, but in reverse way. So that will be the continuity from below type things. So for that case, but we have to show that the countable additivity. That means if I consider a disjoint union of elements, AI sequence of elements which are disjoint, then we have to show that mu of this sum is actually summation. This summation. So let's take E is equals to this set. Now if I take Fn is equals to this one, and then I have to prove that limit n tends to infinity Fn. That is the so that means this means that limit n tends to infinity Fn means E. So but if we switch, like if we take complement in E, then this Gn is nothing but intersection of I equals to n plus 1 to infinity Ei. Okay, so then Gn is decreasing sequence, and that so their intersection is actually basically the empty set. Okay, so now by the continuity from above says that mu of empty is equals to limit and infinity mu of Gn, because their intersection is empty set. That's why it is happening. Okay, because Gn is decreasing as well as their intersection is empty set, because their intersection will give empty set. You can check that one, and so that's why we will get the limit n tends to infinity mu of Gn is equals to 0. Now we can write E as in this form: E minus Fn union Fn, and E minus Fn is Gn. So now as these two are the disjoint, then by using additivity again, we here we have used the additivity of mu. So what we get, mu of E is equals to mu of E minus Fn plus mu of Fn. So now the left hand side is mu of Gn, and so therefore right hand side is, so if you take the limit n tends to infinity, right hand side I will get the whatever the desired things that I will get, and then we'll conclude the things here. Okay, so this is what it is getting. Okay, so now let's go to some another problem. Okay, so here is an let's write a question here. Let R be a ring. That means again ring means this is closed under difference and union. Ring of subsets of a non-empty set X. Let mu be a measure measure on R if E and F belongs to R, so that mu of E plus mu of F is equals to mu of E union F plus mu of E intersection F. Okay, this is very easy, not a big deal, and this is also expected. One can think of, let R be the ring of subsets of non-empty set and mu be a measure it is given. So as mu is measure, as mu is measure on R, then for any two disjoint set, any two sets y1, y2 coming from the set R with the condition y1, y2 is equals to empty, mu of, mainly countable subadditivity will be there, but I need the finite additivity is on okay for me. Y1 in union y2, that is equals to mu of y1 plus mu of y2. Okay, so now one can write E union F, that is equals to this way. E union F can be written like, and so okay. So now using this one can write also that for any set Y, okay, one can write Y1 is equals to Y1 minus Y2 union Y1 intersection Y2. I think one can write this. Okay, one can write this way. And here y1 minus y2 and y1 intersection y2. And here y1 minus y2 and y1 intersection y2 are disjoint. Okay, that's true. So therefore what we can write is that mu of y1 is equals to mu of y1 minus y2 plus mu of y1 intersection y2. So therefore just a minute. If y1 and y2 are no, this is the disjoint, then we can write this one thing. Another thing is that to prove this one, what I need to do is some way. If I can write, so if I can write E union F is equals to E union F. Okay, so it can be written as E minus E intersection F first place union F minus E intersection F union E intersection F. These are the disjoint union one can write. Okay. Note that for any E and F belongs to R, this is disjoint union. This is disjoint union. Okay. Now then additivity of mu gives that mu of E union F is equals to mu of E minus E intersection F plus mu of F minus E intersection F plus mu of E intersection F. So to prove the claim, to prove the solve the problem, it is enough to prove to solve the problem. It is enough to show that solve the problem it is enough to show that mu of E minus E intersection F is equals to mu of E minus mu of E intersection F. Okay, but this is the case. Why this is the case? Because E can be written as E minus E intersection F union E intersection F, where E minus E intersection F and E intersection F are disjoint. Okay, so that says mu of E is equals to mu of E minus E intersection F plus mu of E intersection F. That gives mu of E minus E intersection F is equals to mu of E minus mu of E intersection F. Okay, so this is the case. Now I'll do another problem. So this completes the proof. Okay, so another problem. I think this will be take little time. So let's do that one. Try that one at least. Let H be a hereditary sigma ring of subsets of a non-empty set X, and let let mu star be an outer measure on H. If E and F are two elements in this hereditary sigma ring, and if at least one of them is mu star measurable, so that mu star E plus mu star F, the same thing, mu star E mu star F is equals to mu star E union F plus mu star E intersection F. Okay, we have shown this one is the further just measure. Okay, so now I think mu star is an outer measure on H if E and H and if at least one of them is mu star measurable. Here it is interesting fact. What first of all, what is the here is a thing will be little different, but previous thing will be used, but little different here. First of all, what is hereditary sigma ring? That we have to first look at. What is hereditary sigma ring? That a sigma ring is said to be hereditary sigma ring if it is if a set a sigma ring H is said to be hereditary sigma ring, said to be hereditary 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 sigma ring. Sigma ring. If a set E is in H, that should imply every subset will be in H for every subset which is a subset of E that has to be in the set H. Okay, this is the hereditary. And what is called the mu measurable and a element, and this is the first fact. Second fact is that a set E in the hereditary H is said to be mu measurable, is said to be mu star measurable if for any element A in H, mu of A is equals to mu star A intersection E plus mu of mu star A intersection E complementary. Okay, this is what it means, the mu star measurable. Okay, which is equivalent to the fact that, because the additivity is there, which is equivalent to that to okay. So here it is says if at least one of them E or F is Mr. measurable, then so that the other. So let E in the given conditions in the problem is Mr. measurable. In the problem is Mr. measurable. Okay. Now that means for any set A, it will be like this way. Okay, this will hold. Now let's we have to choose a wisely so that we can get these things. Okay, so now what we can choose A. Okay, so if we choose A, if we choose A, if we chose A F, what will get? Mu star F, mu star intersection F, E complementary means how? E complementary means question is that if we choose at least one of them is to put this one. Mr. Union F equals to Mr. E plus Mr. F equals to Mr. A Union F plus Mr. A intersection F. We have H is hereditary sigma ring of subsets extended to show that set to be Mr. Miserable if for any A belongs to Mr. A is equals to Mr. intersection E plus Mr. intersection E complementary that we know. If we choose A equals to E union F, what we have already have the thing is that, so this is what we have to, this is what we know. Is it algebra given? Sigma ring of subsets of non-empty sets X and that must be outer measure on the GK and at least one of them is Mr. Measurable so that Mr. is equals to, okay, 1 minute. Just a minute. Hmm. If we take A is equals to what we should take, that I'm not understanding what we can take here. The outer measure, we have the positiveness, we have the monotonicity, we have the empty set is 0 that we have, but what else we can have? Okay, if I take A is equals to E union F, then E union F intersection E, that will give E itself, and E union F intersection E complementary, union F intersection E complementary, that is not giving anything. Okay, okay, so let me, what I have to prove is that mu of, okay, what I have to prove is that mu of E plus mu of F, mu star of E, mu star of F, mu star of E intersection F plus mu star of E union F. Okay, so mm, in that way, if we replace here E intersection F, mu of E intersection F, mu star of E intersection F, that is equals to mu of E intersection F intersection E, that is E intersection F intersection E, that gives E intersection F again, plus here E intersection F intersection E complement, what it gives, intersection F, that gives empty set. Okay, so that is 0. So this is, we are not getting anything then. So if we replace here E union F, then what I'll get, mu of E union F, then we'll get mu star of E star E union F union intersection F intersection E, that is E again, yeah, plus mu star of E union F intersection E complementary. So what we'll get, E union F, E union F is the this one, and with E complementary, that is will be, that gives F minus E intersection F. This is what it will give. But F minus intersection F means, okay. Hmm. Okay, so I'll do this later. incomplete. This is incomplete. I'll do another problem and close today's session. This is incomplete. I'll do it in the next day. Okay, so I'll do another problem and so question is that let R be a ring of subsets of a non-empty set X. Define the subring that is in the sigma algebra. So that is collection of all subsets such that F is equals to R or FC is belongs to R. So R is a ring. R is already being given, and S is the collection of sets such that F is belongs to R or F complementary is belongs to R. So that this is the smallest algebra containing R. So that S is the smallest algebra containing R. So basically here note that S is closed. I mean it will take all the elements of R as well as complements of elements of R. That it consists all the elements of R as well as all the elements from the complement of R. Complements of elements in R. Complements of elements in R. All the elements complements of elements in R. Which are complements of elements in R. Which are complements of elements in R. So this is the case. Okay. So let's. So this is the case. So what I have to put the S is the first of all algebra. First of all, this is the algebra, and this is the smallest algebra. So let's check. So let's check whether S is an algebra or not. So first we show that S is an algebra. So for that, what I have to that so that S is a. So let's note that phi belongs to R. That implies phi belongs to S, and that also belongs phi complementary, which is actually the full set X, that is again in S. Okay. Secondly is that it is ring or not. Okay. So if E and F two element is in S, okay, that means what I have to show, that is closed under union, that is either E or E complementary is in R, and F or F complementary is in R. So then those element E or F will be there. Okay. So now what you have to show that their union is there. We need to show that their union is there. Belongs to S. So that their union, okay, where if E is belongs to R and F belongs to R, then their union. So there is four case. Okay, first first case, E belongs to R, F belongs to R. In that case, E union F belongs to R because R is ring which is subset of R. Second case, E belongs to R, F complementary belongs to R. In that case, E union F which is equals to, which can be written in the way that E union F complementary is there. I have to show E union F is there, right? E and F is there, then I have to show E union F is there. E union F can be written as no. This is E, this is F. I have to show the full thing is there. So initially it is giving that E is there and it is there. So how can I write question is that R is the ring of subsets of non-empty set X. If an S equals to say so, thus F belongs to subset of X, either F is in R or F complementary is in R. So that S is the algebra containing R. S is containing R, that's okay. But this is the smallest algebra containing R, right? That is the question. This is the smallest algebra. Smallest algebra containing R. To prove the algebra, we first need to prove that this is a ring, and as well as empty set and countable identity will be there. Okay. So union, for to prove that union is there. So let's take two element E and F is there. That means either E is there or if complementary is there. So in that case, E union F can be written as E F complementary, E complementary union F whole complementary. That's okay. No, 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 no. Okay, as E is there, F complementary is there. So E intersection F complementary is there. That is E minus F is there. S is closed under, okay, S is closed under union difference, symmetric difference. Sorry. So F is there. So E intersection F complementary is there. E union F complementary is there. E intersection F complementary is this. E union F complementary is this. E minus F complementary. Sorry. So as E and F, okay, separately if we can show, then it will be so. So as E belongs to R, F complementary belongs to R, E minus F complementary, which is equals to E minus F complementary, which is equals to E intersection F. You can look at the E minus F complementary. F complementary is the outside region and E is this region. So E minus F complementary means it will go this way. So it will be there. It will belongs to R, and as well as E symmetric difference of these two, as well as E minus E intersection F complementary is there, but that is equals to E minus F. E intersection F complementary, that is equals to E minus F, that is there. And next is that F minus E complementary, that will hold because as these two is there, E complementary and F is there, and that says that E complementary intersection F, that is equals to F minus E, that is there. So that implies that E union F, that is equals to E intersection F union E minus F union F minus E. This is also in R. So that means this is in S. Okay. So similarly, other two will hold. So that if E union F is in S. Okay. So first of all, union, it is closed under union, and difference will also be similarly. One can show that the difference is also whole. Similarly, one can show that differences is there. Okay. So first of all, why this is smallest? This is the last question. So question is why this is smallest? Why this is the smallest algebra containing this? Okay. So now, for this to prove that if any algebra contains S, that should now why S is the smallest algebra containing R. So enough to show that any algebra, any sigma algebra, I think the term is written as sigma algebra, smallest algebra, right? Smallest, any algebra containing R must, any algebra, so it is enough to show that any algebra, so that any algebra containing R must contains S. Okay. So if S prime is an algebra such that R must contain in S dash, then as it is algebra, it should contains, as S dash is an algebra, so X will be there. So X will be there. Okay. That implies as that implies for any E belongs to R, X minus E, that is equals to E complete, that has to be in S, because S is an algebra, so that has to be ring, because S is an algebra, so it is necessarily ring. So it closed under difference, closed under differences. So for any E belongs to R, its complement is again in S, because that has to be, because S has to be closed under difference. But as X in the S dash, so and E, if E is in R, that means E is in S dash. So therefore, because R is subset of S dash, therefore X minus E complement has to be there. So that means for any E belongs to R, E complementary also has to be in S dash. That implies S is actually subset of S dash. That implies S is the smallest algebra algebra containing R. Okay. So just one, if we want to, so interesting fact is here is that if you want to add only one extreme element to have to make in an algebra, that is the X. But for that you have to at least add all the complementary of the elements in R. Okay. So I hope this is okay. This is all for today. So in the next class, in the next tutorial, I'll try to be more prepared and I'll try to collect more problems so that it will be good, I believe. So for today, this is all, and for the next tutorial, I will be try to be more more smooth and more problem. I'll try to collect more problem. Okay. So that's all. I'll stop here.